Welcome to Unit 14, Video 1, Enthalpy of Reaction. By the end of this video, you should understand the concept of enthalpy of reaction and what it represents. You should know what an enthalpy of formation represents. And you should be able to calculate the enthalpy of a reaction from standard enthalpies of formation. Recall that enthalpy, represented with a capital H, is the energy content of a system at constant pressure. But since we almost always work at constant pressure, for our purposes, enthalpy will be pretty much the same as energy. We'll use those terms sort of interchangeably. An enthalpy change, represented by delta H, is the difference between the enthalpy of the reactants and the enthalpy of the products in a reaction. In other words, at constant pressure, the enthalpy change is equal to the amount of energy absorbed or released by a chemical reaction. Recall that we almost always work at constant pressure, therefore, we'll treat enthalpy change as the amount of energy absorbed or released in a reaction. As we've discussed before, delta H, or enthalpy of reaction, represents the difference between the energy required to break bonds in the reactant molecules and the energy released when new bonds form in the products. Looking at the diagram on this slide, we see a picture representing the reaction between 1 mole of CH4, 2 moles of oxygen, and yielding 1 mole of CO2 and 2 moles of water. Notice in the picture, we have to put energy in. Energy in is represented by the red arrow, so we have to put energy in to break each of the bonds in the reactant molecules. On the other hand, in the products, when new bonds form, energy is released. So these blue arrows represent energy that comes out when new bonds are formed. Therefore, the difference between the energy that went in to break reactant bonds and the energy that came out when product bonds form represents the delta H of the reaction, or the enthalpy of the reaction. Notice that in this case, less energy went in than came out. Therefore, this reaction is exothermic. Overall, it releases energy. Reviewing quickly our vocabulary, recall that exothermic reactions release energy and have a negative delta H, and endothermic reactions absorb energy and have a positive delta H. Now we want to be able to quantify these enthalpies of reaction. Enthalpy of a reaction is a state function. A state function is a property of the system that depends only on its present state. In other words, it's independent of pathway. So it doesn't matter how you get from point A to point B. All that matters is the difference between point A and point B. Energy change in a chemical reaction is a state function. In other words, the same amount of energy is gained or lost regardless of the pathway the reaction takes. This allows us to calculate delta H for a reaction in many different ways. In this class, we're going to learn a few different ways to calculate delta H. First, we can do it stoichiometrically, which we looked at in the previous unit. In this video, we're going to look at how to use standard enthalpies of formation to calculate delta H. In the next video, you'll look at Hess's law as another way of calculating delta H. And finally, in lab and in the fall, we looked at calorimetry as a way of measuring the energy change during a process. Let's look now at how to use standard enthalpies of formation to calculate enthalpy of reaction. Standard enthalpy of formation is represented by delta H, small f, and a degrees sign. The degrees sign represents standard. Standard enthalpies of formation are the amount of energy consumed or released when 1 mole of a substance is formed directly from its elements in their standard states. Don't get too hung up on what standard states are. Generally, it just means the reactants in their elemental form at roughly room temperature. So, for example, the delta H of formation, or the standard enthalpy of formation of carbon dioxide, is negative 393.5 kilojoules. In other words, when 1 mole of CO2 is made directly from solid carbon and gaseous oxygen, 393.5 kilojoules of energy are released. Recall, as we learned in the last unit, that this relationship is stoichiometric. In other words, if 2 moles of CO2 is made directly from solid carbon and gaseous oxygen, then 2 times that amount of energy are released. Here's a table representing standard enthalpies of formation of several different compounds. Note this is only a small selection. You'll be given this table whenever you're asked to calculate enthalpy of reaction using standard enthalpies of formation. This table is also posted on Haiku. Now might be a good time to access this table and print it or download it because you'll need it to do the practice problems. It's also important to note that pure elements, including the Hofbrinkels, will have a delta H of formation of 0. Consider the fact that pure elements can't form directly from their elements because they aren't compounds. Therefore, they have a delta HF of 0. Now we can use this information to calculate delta H. Since delta H is the difference between the energy absorbed when reactant bonds are broken and the energy released when product bonds are formed, the delta H is essentially the difference between the two. Mathematically speaking, we can represent this relationship as follows. The delta H of reaction is equal to sigma, which means sum, so the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. These values will all be found on your table, or they'll be given to you in the problem. Let's look at an example. Here we're asked to calculate the delta H for the following reaction. Notice this equation is balanced. That's important. As we just saw, the delta H is going to be equal to the difference between the sum of the delta H of formations of the products and the sum of the delta H of formations of the reactants. I'm going to start by calculating the sum of the delta H of formation of the products. I like to do each one separately so we don't get confused with the math. Our products in this case are CO2 and water. Here, from our table, we know that the delta H of formation of CO2 is negative 393.5, and the delta H of formation of H2O in its liquid form is negative 285.8. But since there are 2 moles of water, we need to multiply this value by 2. In total, we'll have a delta H of formation of products of negative 965.1 kilojoules. In other words, when these products form, 965.1 kilojoules of energy will be released. Turning now to our reactants, CH4 and O2, we see from our table that the delta H of formation of CH4 is negative 74.8, and recall O2, since it's a pure element, will have a delta H of formation of 0. In total, then, these reactant bonds will require 74.8 kilojoules to be broken. Putting the pieces together, we subtract our delta H of formation of our reactants from our delta H of formation of our products, and we get a delta H of negative 890.3 kilojoules. In other words, when 1 mole of CH4 reacts with 2 moles of oxygen to form 1 mole of CO2 and 2 moles of liquid water, 890.3 kilojoules are released. Recall, we can write this in as a product, since it is an exothermic reaction. Here's 2 to try on your own. Pause the video here and use your table of delta H of formations to calculate the delta H for each of these reactions. Notice that they're each unbalanced, so you'll need to balance the equations before you proceed. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. That brings us to the end of this video. Let's review our goals. First, we looked at the concept of enthalpy of a reaction, the difference between the energy required to break reactant bonds and the energy released when product bonds are formed. Then, we looked at enthalpy of formation. This is the energy change associated with the formation of 1 mole of a compound directly from its elements. And finally, we looked at how to calculate the enthalpy of a reaction using standard enthalpies of formation